Hello, and welcome one more time to another lesson with Dr. H. On today's lesson, we're going to try to crash our way through some Wigger's diagram. Hopefully, I can help you cram for your tests and help you learn a little bit more about how the cardiac cycle works and what exactly the Wigger's diagram is a representation of. So first off, when you look at the Wigger's diagram, you're going to notice a couple of aspects of it that you might want to try to draw down. The very first thing that you're going to want to try to draw down is the EKG. So EKG, we're just going to try to do a quick representation of the EKG. So just draw that flat line, the first bump, right? Flat line. The QRS complex. That leads in the last thing. So let's go ahead and go through and label this curve because that's what we want to try to do, one step at a time. First portion is the P wave. Okay, this flat line in between was that PR segment. PQ segment is another way to look at it. The second landmark is the Q, R, S. Those three things together are the QRS complex. And finally, the T wave. The area from the end of the T to the beginning of that P, that was the TP segment. From the end of the P to the beginning of the Q, that's the PQ or PR segment. And from the end of the S to the beginning of the T, that was the ST segment. Now, when you look at the Wigger's diagram, what you see is a representation of a curve that has pressures and volumes. And the reason for that is because what we're after when we think of cardiophysiology, what we're after when we're thinking of the function of the heart is how much blood does this heart pump out as it contracts? And then how much blood does that heart fill with as it relaxes? So imagine chambers that are getting pressurized. And as they get pressurized, that's going to drive blood flow from areas of high pressure to areas of low pressure. And that's what we're after with this curve. Okay, so let's try to draw this out real fast. I'm not going to dawdle around too much. We're going to have a pressure curve. X-axis typically is over time. The y-axis is going to be pressure. And we're typically talking about left ventricular pressure in millimeters of mercury here, or left side of the heart pressure in millimeters of mercury. The first portion of the curve that I'm going to go ahead and draw in pencil, and then I'm going to mark over it with a marker, is going to be atrial pressure. And atrial pressure is going to run between, I said atrial pressure, aortic pressure, and aortic pressure is going to run between 120 millimeters of mercury to 80 millimeters of mercury. Think of this as your systolic blood pressure, and it's extremely helpful. So atrial pressure during a cardiac cycle is going to start around 85 to 90 millimeters of mercury, and it's going to slowly decrease before increasing. That's as blood gets ejected out into it. Then you're going to get a little bump. This is called the dicrotic notch. This is actually going to occur as valves slam shut, and then blood basically gets some backflow, and that's going to cause this little jump in pressure inside of the aorta. And then finally, it's going to end up kind of just decreasing again over time. Did I get that high enough? I'm not sure I did. So let's go back. We want to make sure that this aortic pressure gets all the way up to 120 millimeters. So let's make sure we get up there. Okay, and then it's going to come back down to approximately 100 millimeters of mercury or so. And that's when we're going to get this dicrotic notch. See, it's important to go through. You make mistakes, you redraw it out. And this will help you learn how this entire system works. So this is going to be what's happening with the aorta. And we're going to go ahead and label this red because it's easier that way to be able to see and color code what's happening. Okay, The next portion that we want to look at in terms of pressures, not what's happening in the aorta, but we also want to look what's happening in the left ventricle. Well, left ventricular pressure starts extremely low. We're talking around 10 millimeters of mercury or so. Okay, and left ventricular pressure is going to be kind of stable, 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 until the atria contracts. And when that atria contracts, a little bit of blood from the atria goes basically ejecting, right? A little bit of blood from the atria is going to get pushed down into the ventricle, and you're going to see a little bump on the Wigger's diagram. And that's just a representation of blood entering that left ventricle. After that point, the ventricle is going to start to contract. And as it contracts, it's going to shoot up and up and up. Okay, and that ventricular pressure is going to eventually get greater than aortic pressure, and that's going to be important, at which point this curve is going to start to round out, and then it's going to end up dropping back down again as the ventricles contract, as the ventricles relax. Okay, and that's going to allow ventricular relaxation to drop that pressure of that left ventricle all the way back down again. And it's going to reach almost zero before leveling out and coming back up on the other side. So let's go ahead and draw this in with the color blue. And this is going to be a representation of ventricular, left ventricular pressure is what we're going to focus on. The red line is aortic pressure. And the blue line is going to be ventricular pressure. Left ventricular pressure to be specific. Now we need to add one more line to this thing, and that's going to be a representation of atrial pressure. And atrial pressure is going to start out greater than left ventricular pressure, and that's kind of important. Okay, it's going to start out slightly greater, just a fraction greater. And then as the atria contracts, of course, pressure inside of that atria is going to go up. But what's going to end up happening is that as ventricular contraction occurs, well, the ventricle is made up of so much more muscle than the atria, that ventricular contraction is going to overcome the atrial pressure very, very easily. And the atrial pressure is going to just, well, not really do much more. It's not going to really do much more. At first, pressures are going to be a little bit high because of the pressure getting pushed back. But the second that the ventricular pressure gets over aortic pressure, what's going to end up happening here in the atria is that it's going to just start to relax. And as it relaxes, it's going to passively fill with blood. So this value now here is going to just slowly increase as pressure is going to increase inside the atria because it's slowly filling with blood. But eventually ventricular pressure is going to drop back below atrial pressure, at which point, you guys are going to learn more about this in just a second, but at which point a valve is going to open and all of that blood that was filling up inside the atria is going to be dumped off into the ventricle. All right, but it's important to note that atrial pressure at this point is going to be greater than ventricular pressure. So let's draw the blue line in, or sorry, the green line in. And this is going to be atrial pressure. At the beginning of the cardiac cycle, it is above ventricular pressure. During ventricular contraction, ventricular systole, it's going to remain below ventricular pressure. And after the ventricles have relaxed, so during ventricular diastole, at some point during ventricular diastole, the atrial pressure is going to become greater than the ventricular pressure again. Okay, those arrows over there are a little confusing, aren't they? So let's go ahead and put in left ventricle and underline it as blue so you guys can follow that along. Versus the green line is going to be a representation of the left atrial pressure. So let's put that in over here. And we'll go ahead and underline that green so that you guys can keep your color codes all lined up. This is what the pressure portion of the Wigger's diagram looks like. Okay, and now you can kind of see what's going on, and we're going to combine that with what's happening with the EKG in just a second. In addition, we're going to try to combine that with what's happening with the volume of blood inside of the heart. Because really, it's about pressure-volume relationships, not what's just happening with pressure, but also what's happening with the ejection and the filling of blood into that heart. A way that I like to look at this has to do with blood flow through the heart. And this is unique to my teaching style. It doesn't work for everybody. But if you think about how that heart is laid out, right? We know that this heart is going to be, and let me just try to draw this out really quick. Right. We have ventricles down below. We have the atria up above. We want to try to draw this as a cross section. We're going to have the interventricular septum run up. We're going to have the left ventricular wall. And we're going to have some valves that drop down. Up above is going to be the different atria. Up above is going to be the different atria. And there's an atrial septum, of course, interatrial septum, interventricular septum down below, and some valves that separate those things. So now I got the right atrium. I got the right ventricle. I have the left atrium, and I have the left ventricle. And if you want to try to think about how heart moves out of this, well, it makes it a little bit more complex because we have to draw the valves that leave the ventricles out into the pulmonary circuit or the ventricular circuit. So instead, what I'm going to go ahead and add in here is a little flow chart that talks about the flow of blood through the heart. But we're going to focus on the left side of the heart. So we know that blood is going to move from the left atria, and that blood is going to move into the left ventricle. And from the left ventricle, that blood is going to move where? Into the aorta. And in order for blood to move from the left atrium into the left ventricle, and from the left ventricle into the aorta, they're going to have to be moving through some valves, right? That's why the arrows move in one direction. They're not going both ways. Blood flows one direction through the heart, and it has to do with the valves that are in place. So from the left atrium to the left ventricle, we have the mitral valve, otherwise known as the bicuspid valve. And from the left ventricle into the aorta, we have the aortic valve, or the aortic semilunar valve. We're just going to go ahead and write in AV. So this is a nice quick flow chart to help you understand blood flow through the heart and how valves lie in between. So now let's think about pressures. If the left atria has a greater pressure than the left ventricle, so left atrial pressure is greater than left ventricular pressure, what do we know about the mitral valve? Will it be open or will it be closed? Well, due to the anatomical features of the mitral valve, it only opens in the direction from the left atria to the left ventricle. Blood can only flow this way. So if left atrial pressure is greater than left ventricular pressure, then the mitral valve will be open. But what if left ventricular pressure is less than aortic pressure? And we're just going to write aorta because it's easier that way. Well, what do we know is going to happen there? Well, if the left ventricle has less pressure than the aorta, what's going to happen to the aortic semilunar valve? Well, there's not enough pressure here to open that valve. So this valve will be closed. So what do we know about the mitral valve? And what do we know about the aortic valve? Sorry, I'm running out of room over here. The mitral valve will be open. And we're just going to write O, and the aortic semilunar valve will be closed. So we're going to write C. Cool. And let's go back over here and look on the curve on the Wigger's diagram. Where is left atrial pressure greater than left ventricular pressure? And this is where the colors come back into play. Where is left atrial pressure greater than left ventricular pressure? Anytime the green is greater than the blue, right? So left atrial pressure is greater than left ventricular pressure, all here and over here. So what do we know about the valves in that scenario? The mitral valve will be open here and the mitral valve will be open here. Does that make sense? I hope so. What about aortic pressure? When is left ventricular pressure less than aortic pressure? Anytime that the blue line is below the red line. So all throughout here, the blue line is below the red line. Over here, the blue line is below red line. So all of this period of time, the aortic semilunar valve will be closed. What's going to happen now as the heart starts to contract? What's going to happen as ventricular pressure starts to increase right here on the curve? Well, the left atrial pressure will become less than the left ventricular pressure. But right here on the curve, left ventricular pressure is still less than aortic pressure. So what do we know about the valves? The left atria is less than the left ventricular pressure, therefore there's not enough pressure to keep that mitral valve open, therefore it closes. And not only does it close, but it slams shut. And this is going to be S1. This is the lub-dub, lub-dub. This is the lub of the heart sounds. Now, what do we know about aortic pressure? It's still greater than left ventricular pressure, so the aortic semilunar valve will still be closed. In this scenario, right here, when the blue is greater than the green, but the blue is still less than the red, all valves of the heart are closed. We call this isovolumetric. And since this is occurring during ventricular systole, we call it isovolumetric contraction, or IVC. Let's go ahead and put in our color code. I don't know why I got to do this. It helps me study. It helps me retain this information. And I hope it does the same thing for y'all. Let's do one more scenario here. What about way up here? Right? The heart just keeps contracting. The left ventricle keeps contracting. This is a big muscle, so it's going to contract, contract, contract until finally, and at this point, right, left ventricular pressure is still greater than left atrial pressure. I started writing that wrong. That's all right. We'll color code it. But now left ventricular pressure is going to get greater than aortic pressure. What's going to happen now? At this point, the mitral valve is still closed, right? Because left ventricular pressure is greater than left atrial pressure. But when the left ventricular pressure finally gets greater than aortic pressure, then the aortic valve gets to open. All right, at which point blood can finally move from the left ventricle into the aorta. At this point is when blood finally gets to move from the left ventricle and the aorta. Therefore, blood is going to go rushing out of the heart. All of this pressure built up during the IVC, and now this blood gets pressurized out of the heart. This is called ejection. This is called ventricular ejection. Okay, ventricular ejection. There is a rapid portion of ventricular ejection and just a little bit slower portion of ventricular ejection over here. So FVE is fast ventricular ejection. SVE is slow ventricular ejection. If you are required to learn those things, hopefully that helps. But now the heart is going to start to relax because ventricular diastole is going to start up. Okay, the depolarization of the ventricles stops. The repolarization of the ventricles begin. And as they are repolarizing, they start to relax. Once they've completely repolarized, all those muscles are relaxing. So now the ventricular pressure is going to decrease, 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 decrease. And now we just move our way back. We go down first, right? Step 1, step 2, step 3. But then step 4 is back here, and finally we're going to be over here. So if we go step 1, step 2, step 3, well, as the heart relaxes, we're just going to go backwards. Because ventricular pressure is going to get less than aortic pressure, but that's what we have right here. Left ventricular pressure is still greater than atrial pressure. So what do we know about the valves? At this point right here, we're going to have a scenario now that is identical to a previous scenario where we have all the valves of the heart closed. Left ventricular pressure is less than aortic. That's where the aortic semilunar valve slams shut. That is S2. That's the second heart sound. But left ventricular pressure is still greater than left atrial pressure. Therefore, the mitral valve is still closed. This is isovolumetric. Iso means same. Volumetric tells you volume. This is still IV, but now it's during relaxation, so we call it IVR. That heart is going to continue to relax as it goes through ventricular diastole. It's going to relax, relax, relax until finally ventricular pressure, which is already below aortic pressure, finally that left ventricular pressure is going to drop back below left atrial pressure, and we're back here again. Okay, now we're back here again where the left atrial pressure becomes greater than left ventricular pressure, but left ventricular pressure is less than aortic pressure. So what do we know about our valve situation? The mitral valve is going to open at this point. The AV valve is still closed. So we're going to have 4 locations where valves are going to open and close. 4 locations where valves are going to open and close. And that's what we have going on right here. Okay, so it's step 1. That doesn't match with step 1 over here. So we're going to actually write a separate step for this. At step 1, step 2, step 3, and step 4, we need to be thinking about valves. At step 1, what do we know happens? This is when the mitral valve slams shut. This is S1. At 2, the mitral valve is still closed, but what's going to happen at step 2 when ventricular pressure gets greater than aortic pressure? That's when the AV valve, the aortic semilunar valve, that's when it opens. Should not hear a sound here. If you do, we got some issues. 3, when ventricular pressure drops back below aortic pressure again, what's going to happen? That AV valve is going to close or slam shut. Therefore, when you slam a door, you get a sound. And then at 4, right, this is just where these curves are crossing. Left ventricular pressure gets less than the aortic pressure. Therefore, the mitral valve is finally going to get to open. So that's what we want to think of when we're thinking about the Wigger's diagram. We don't want to just say, what does graph, right? What's it doing? This is a representation of what valves are doing based on the pressures. That's what the Wigger's diagram is trying to do. And then it tries to connect it to the EKG. So at the beginning of this entire mess, we wrote down the EKG. Well, how does this help us understand this? Well, this is a cardiac cycle. The P wave begins when the atria starts to depolarize. So this P wave is a representation of the atrial depolarization. Well, what happens at the end of atrial depolarization, right? What is this PR segment a representation of? If you've seen my previous videos, you know this already. Well, that's when the atria is contracting. So that's atrial contraction right there. The QRS is when the ventricles are depolarizing and they are starting to contract during that RS. And then they continue to contract very heavily through the ST segment. So that is going to be indicated that R to S, that's when these ventricles are contracting. And then it continues to contract through the S and the T. And that's what you see with this ventricular ejection. The RS is the IVC region, and the ST is when blood is ejected, physically ejected from the heart. The next portion of this is the T wave. And during the T wave, that's when the ventricles are repolarizing. They're still contracting ever so slightly. So that's going to be the very end of ventricular ejection. That's kind of a slow ejection phase, the slow ventricular ejection. Finally, though, once they repolarize, they're going to start to relax. And that's what's going on in the TP, right? From the end of the T wave to the beginning of the next P, we're going to have diastole that's occurring. And during the very beginning of that portion right here, that is when we get the IVR. That is isovolumetric relaxation as it relaxes. Finally, when the left ventricular pressure gets less than the atrial pressure yet again, then the ventricle starts filling with blood. This is ventricular diastole as it refills with blood. And that is the rest of that TP segment. Hopefully that helps you guys understand that portion of the Wigger's diagram. The last portion of the Wigger's diagram that's important to understand is how does pressure relate to volume? Once you understand how pressures work and how valves open and close, in my personal opinion, the volume becomes a lot easier to understand. Because volume is being ejected out through this cardiac cycle, through this time frame. But now we're going to be dealing with volumes in the heart, and volumes tend to be measured in milliliters in the body. All right, what do we know is going to happen to blood volume during ventricular diastole? Well, ventricular diastole is all about the heart filling with blood. Right? We want this thing to be filling with blood during diastole. So at the very beginning of the curve here, we are going to have approximately, and this just depends on the patient that you're dealing with, but there's approximately 120 mils or so of blood inside of the heart. So at this point, the heart is still filling with blood. So this curve is going to be slowly increasing, very slowly increasing. What's going to happen to the, by the way, I'm so sorry for not mentioning it. I'm talking about left ventricular volume here, LV volume. That's what we really care about. That's the blood that gets pushed out to the systolic circuit. So during atrial contraction, I mentioned previously, is that as the atria contracts, a little bit of blood is going to move into the left ventricle. And that's going to be the last little bit of blood that now enters that left ventricle. And we can start lining this up, and I'll do that using pencil. That at the beginning of atrial contraction, we're going to get a little burst of blood that is going to enter that left ventricle. And it's going to continue to increase the volume until the ventricle starts to contract. This right here is the maximum volume of blood inside of the heart at the end of ventricular diastole. We call this volume of blood right here end diastolic volume, EDV, where EDV is the maximum volume of blood. At the end of diastole. Easy peasy. Now, what do we know is going to happen? There's going to be a period of time when the ventricle is contracting, but the aortic valve is not opening. where all the valves in the heart are closed. And we called this isovolumetric. Why did we call it isovolumetric? Because during this time, and I'm not sure I'm lining that up properly. I'm not sure I gave myself enough room. Close enough. During this time right here, no blood is leaving the heart. So this portion of the curve is a representation of the isovolumetric contraction. No volume changes at all. By the way, EDV tends to be about 130 mils on average in your patients. But now, when ventricular pressure gets greater than aortic pressure, blood gets to rush out of that ventricle into the aorta. So what's going to happen to the ventricular volume during this time? It's going to decrease. How long is it going to decrease? Well, it's going to continue to decrease until the aortic semilunar valve closes again. So let's go ahead and draw a dashed line down. And the minimum volume inside of the heart, we're actually not going to go to 0, 0 down here. We're going to say that this corner of the curve is approximately, we'll go ahead and say 60 mils. So instead of being a 0, 0, we're going to actually have the bottom left-hand axis of our graph be 60 mils. And during contraction, at the end of contraction, the heart tends to have about 70 mils of blood left over. So we're going to go ahead and have this dashed line go down to about 70 mils. So now as the heart contracts, we're going to get a period of rapid ejection of blood, which is going to slow down and level off. This is what's happening during the contraction of heart. And at the end of systole, there's going to be a volume of blood left over inside of the heart. What do you guys think that volume of blood is going to be called? This is end systolic volume. This is end systolic volume. That's going to equal the minimum volume of blood. There's still some left over. Actually, there's more than half of the volume of the heart that's left over. We always want to have some leftovers at the end of systole. All right, but then what's going to happen? At the end of systole, we're going to get a short period of time when all the valves in the heart are closed. That's going to be a representation of this portion of the curve. So that is going to be IVR, right? That is isovolumetric relaxation. Isovolumetric, no volume change. But then ventricular pressure is going to get less than the atrial pressure, and the ventricle can start to fill with blood again. And that is going to be a little bit rapid at first because the blood is going to passively flow from the atria up into the ventricles, but then it's going to start to level off. And that's going to just go from one cardiac cycle, the end of one cardiac cycle, to the beginning of the next cardiac cycle. So we just go from here to here. All right. End diastolic volume, the average EDV in a patient is approximately 130 mils. The average end systolic volume is approximately 70 mils. So what does that tell us? What's the importance of those values? Well, if we say there's a certain volume at max and a certain volume at min, then we can calculate how much blood ejected during a single cardiac cycle. And if you listen to my lectures before, that's called stroke volume. Okay, so we're going to have SV, stroke volume, which by definition is the volume of blood ejected in a single cardiac cycle. So what equation can we use to understand this better? SV equals max volume minus min volume, or EDV minus ESV. That's going to give you stroke volume. And that's the events of the cardiac cycle. And that's how the Wigger's diagram is going to help relate the EKG with ventricular pressures with ventricular volumes all related to valves being open or closed, allowing for blood to flow. So as pressures change, the valve placement, the valve either being open or closed, will change, and that is going to change how much volume can leave the heart at any given part of the cycle. All right, that's the end of my little shortened lecture on the events of the cardiac cycle. Hopefully that was helpful. Hopefully that's going to help you cram for your exam or study for your exam appropriately. Hopefully you're giving yourself enough time. Likely not, though, which is okay. All right, this is Dr. H. Humankind be both. See you in the next video.